Hello! This video is for Module 1 Part 1 and includes an introduction to Predictive Analytics. Okay, let's go ahead and get started then. So, in order to complete the notes, you're going to want to go to statsclass.org, and you can see here the course materials. There's a link for the notes. I'm going to go ahead and click on that. There are going to be embedded questions within these notes, and you're going to need to submit your answers to these embedded questions. However, notice at the top that there is not a Submit Notes button. And the reason there is not is because you need to be logged into your account before clicking on the notes. So in order for you to submit the answers to the embedded questions within the notes, you need to be logged into your Stats Class account. So let's go ahead and log in. And now you can see that I've been logged into my Stats Class account. And now when I click on Notes, there's going to be a Submit My Notes button here for you to submit your answers to those embedded questions. So again, before you start your course notes, you're going to have to be logged into your account at Stats Class. Okay, let's go ahead and get started then with the Introduction to Predictive Analytics. So the term analytics encompasses a wide variety of analyses that can be done with data. The main purpose of doing analytics is to discover, interpret, and communicate findings from such analyses to help to improve the performance within the organization. There's a particular type of analytics that can be done called predictive analytics. And this is a collection of techniques that use existing data to make predictions for an unknown outcome. All right, let's show you some examples of doing some predictive analytics. Consider the situation where a prediction is needed for the unknown height of two adolescent girls. The predictions will be obtained by considering the heights of 4 other adolescent girls, whose heights are known. So I'm trying to make predictions for these 2 young girls that are behind the curtain here, labeled girl number 5 and girl number 6. In order to help me make those predictions, I'm going to use information from 4 other adolescent girls. So what I need to do is obtain and record the heights of these 4 girls who have known heights. So for example here, girl number 1 is 63 inches tall, girl number 2 is 61 inches tall, girl 3 slightly taller at 70 inches, and then girl 4 here at 57 inches. I'm going to take the information from these 4 girls, which is simply their heights, and use that to make a prediction for these others. I'm going to compute just a simple mean of these 4 heights. So if we do that here, I just add up the 63, 61, 70, and 57 and divide by 4, and I can see that my average height is 62.75. Now that is going to be my best guess for the heights of girl number 5 and girl number 6, is to simply use that average. So we will predict the height of girl number 5 and 6 to be 62.75 inches tall. Now, if we take other information about these girls into consideration, I am likely to improve upon my predictions. So in example number 2, what I'm going to do is take the height of the parents of these girls into consideration. So again, the same setup. I want to predict the unknown height for girl number 5 and girl number 6. But we're going to get information about the heights of the parents from girl number 5 and girl number 6 and use that in our predictions. A quick search of the internet produces the following. It's actually from the Mayo Clinic. And that says here, there's no proven way to predict a child's adult height. However, several formulas provide a reasonable guess. So what they suggest here is add the mother's height to the father's height And we're going to do this in inches. We're going to add 5 inches for boys or subtract 5 inches for girls. So we're doing girls here. So we're going to want to subtract the 5 inches and then divide by 2. So here's the algorithm that is going to help us predict this is actually the adult height. It's not exactly what we want, but it will help us get started. So the adult height of a girl is going to be, again, to take the mother's height plus the father's height, subtract 5, and divide by 2. So in order to apply this or use this equation, again, I'm going to need to know the mother's height and the father's height. So suppose for girl number 5, the mother's height is 64 inches, and the dad's height is at 70 inches. So if I use this formula, I would take 64 plus 70, subtract off the 5, and divide by 2. And I can see that I would predict the height for girl number 5 to be 64.5 inches. The parents of girl number 6 are slightly taller here. The mother is 65 inches tall, the father is 73. So using that same formula, I'm going to predict girl number 6 to be 66.5. Now, these predictions that I have for girl number 5 and girl number 6 are going to be overestimated, because this algorithm here is predicting the adult height, and what I'm interested in is the adolescent height. So these numbers are going to be too tall. This should be what I anticipate this child to be when they're an adult, but I'm interested in the adolescent height. So the prediction algorithm is going to need to be modified in order to make predictions for these younger girls. Again, I'm going to use information from the other 4 adolescents to guide how the prediction algorithm should be modified. Okay, so let's consider some modifications. In the formula provided here, when I'm trying to predict the adult height, I need to subtract 5. If I'm going to try to predict an adolescent height, I'm going to have to use something more than 5 when I'm subtracting. So let's go ahead and use 8. So I'm going to consider one possible modification, and that is to use 8 in this equation instead of 5 in this equation. So here are the girls, again, the 4 with the known heights, 63, 61, 70, and 57. And I'm providing you information about each of these girls' mother's height and father's height. And I have 63.5, 61.5, 70, and 59.5. Now again, this is just my guess for the adolescent height. But I can measure how well my guess is doing. And that idea is the prediction error. So my decision to use 8 instead of 5 was just simply arbitrary. I just tried a different number. And that begs the question, is there a better choice? That is, should I use 9 or 12 or something else here? The concept of prediction error can be used to help identify the best choice for the amount that should be subtracted in order to obtain the best possible predictions. So prediction error is defined to be the actual height minus the predicted height. Again, the actual heights here are 63, 61, 70, and 57. My predicted heights, when I'm using 8 here, are 63.5, 61.5, etc. If I want to try to figure out how much prediction error there is across all 4 of these girls, what we can do is compute what we call the mean absolute prediction error. So what I'm going to do is look at how much error do I have for each of these girls. I'm going to take the absolute value of that quantity, and then I'm just going to compute the mean of those. And this is one of the metrics that is commonly used to measure prediction error. It's called the mean absolute prediction error. or MAPE. So let's go ahead and compute this quantity for the predictions that I have made. So the prediction error here for the first girl is going to be their actual height, which is 63, minus the 63.5. So this minus sign means my prediction was just a little bit too high. Also, on girl number 2, her actual height was 61. I would predict her adolescent height to be 61.5. Again, just a little bit too high. For the third girl, the actual value was 70. My prediction was 70, so I'm right on the mark for that girl. And then for the shortest girl in our set, she was at 57. Predicted height was 59.5. So her prediction error is going to be negative 2.5. Now what we do normally is take the absolute value of those and then compute the mean. So when I do that, negative 0.50 in absolute value is 0.50. I have another 0.50. I have 0 there on that one. That's a perfect prediction. And then for our shortest girl, we were off by 2.5 inches, which is quite a bit. If you take the 0.50, the 0.50, the 0, and the 2.5 and average those together, you get 0.875. So now I have a way to measure how much error on average I have for each girl. Now let's see if we can try to reduce that amount of error. So what I'm going to try next is, instead of using 8, I want to try to use 12. And you can see that for 3 of the 4 girls, I'm still predicting their heights to be a little bit too high. The prediction error here is actually negative 0.50. Here's another negative, and this is another negative. So it appears that I need to subtract a little bit more than 8 in order to try to get these predictions a little closer. So let's try 12. So here you can see that I'm subtracting 12 in the formula instead of the original 5 or 8 that we tried up here above. I'm going to do all those same calculations. I'm going to get the absolute error, and then I'm going to compute the mean of those. And now you can see that my amount of prediction error is actually worse. When I was using 12, my average prediction error is 1.375. When I was using 8, it was only 0.75. So the selection of 12 did not improve things. And in fact, now you can see that I'm actually under-predicting for 3 of the 4 girls here. So let's do one more. Let's try 9. So here I'm subtracting 9 in that formula instead of the original 5 or the 8 or the 12. And after playing around with the numbers a little bit, this is the value. Subtracting 9 produces the lowest mean absolute prediction error. So on average, I'm only going to be 0.625 inches off. This is using 9 is considerably better than using 12, and it's somewhat better than using 8. Okay. So is 9 the best? Well, it turns out 9 is the best. I tried a variety of values in that equation. You can see here from 5 through 13, and 9 produced the lowest mean absolute prediction error. I didn't try half values. I suppose you could try subtracting a 8.5 or a 9.5 to see if that does better. I just stuck to whole numbers here in that equation. If you look at this visually, so if I just take these values and plot those on a graph, we'll see graphs like this throughout the semester or throughout the course. On the y-axis is the mean absolute prediction error, so we want that to be down as low as we can. And you can see that it bottoms out there at 9. And that's the value that I picked up above. So 9 seems like it's the best bet. In this table, I left the 11 blank here. I'm going to leave that for an exercise for you at the end of the notes here. So the best modified prediction formula to use is, again, using the quantity of 9 in there. So now let's use this modified equation for the adolescent height for the 2 girls that I was interested in predicting. So again, if I use the mother height and father height for each of these, and then I'm subtracting 9 here, I'm going to predict the height of girl number 5 to be about 60.5 inches, and girl number 6 to be about 62.5 inches. Okay, some comments about example number 2 here. In order to make predictions using this formula, we need information about the mother's heights and father's heights. If I don't have information, for example, about the father's heights, I'm not going to be able to use this equation to make predictions. I use the mean absolute prediction error here to measure our accuracy. There's other metrics that can be used as well, and we'll discuss those throughout the course. I can compute the prediction accuracy when I have the actual heights. Okay, so when I was trying to, I'm not going to be able to predict, I'm not going to be able to calculate the prediction accuracy if I don't know their actual heights. The formula, right, for the mean absolute prediction error requires us to know the actual and predicted values. So I don't actually know what the amount of error is in my predictions that I'm making for these unknown heights. Now, certainly this formula was based on information from the other girls. The other girls had an average or a mean absolute prediction error of 0.625, so a little over a half an inch. So it is reasonable to assume that the amount of error that I'm going to have in these predictions is probably around that 0.625 inches. All right, let's do example number 3. We're going to do things a little differently here. And here what I want to do is predict one's gender based on their height. So here I just have 3 females. I have 3 males. Generally speaking, males tend to be taller than females. So again, if I have a gender here that is unknown, so I do not know the gender of the person behind the curtain here, but what I'm going to do is use this person's height to help me decide whether or not this person is likely to be male or is this person likely to be female. Now in this silly little graphic here, you can see that the height looks more like the heights of these 3 men than it does of these 3 women. So the gender, I'm going to predict the gender of this person to be male. Again, because this person's height more closely resembles the heights of males. Now, I can certainly be wrong in that, right? Okay, so I could be wrong. This person could actually be just a taller female. All right. So again, we have to realize that no predictions are perfect, and there's going to be situations where predictions are much harder than other situations. For example, if we were to consider the expanded gender categories as females, males, and those that identify as non-binary, this prediction problem becomes much more difficult. So the non-binary group is going to have individuals of varying heights. Okay, so it's going to be much harder. Is this person, can we identify them as non-binary, or should we identify this individual as a male? Or like I said before, maybe it's just a really tall female. So this makes that prediction problem harder when you have a situation like that. How about some more definitions? So there are a wide variety of variables or features that are considered when solving a predictive analytics problem. The communication regarding how the variables are being used in solving the analytics problems is important. The response variable is the main variable being considered. And this is the variable for which you are trying to make predictions for. The other information, okay, the other variables are called the predictor variables. Now, unfortunately, this naming convention is not universal. And there's a lot of different terms that get used in this context. So I will probably refer to the variable that we want to use prediction or do predictions for as the response. But other people might refer to that as the dependent variable, or the y variable, or the output variable. The variables that are being used to do the predictions might be referred to as the independent variable, the x variable, the explanatory variable, or the input variables. Again, there's a variety of language that gets used in this context. More than likely, I will stick to the terms response variable and predictor variables. So let's look at example number 2 again, where we were trying to predict the heights of the adolescent girls. The response variable in that example is going to be the heights of the adolescent girls. Now I had 2 predictor variables. I had the mother's height and also the father's height. In example number 3, what I was interested in doing is predicting the gender. So my response variable there is gender. And the predictor variable is height. Okay, so let's talk about the tasks that I would like you to complete. So I'd like you to complete the following things here. I want you to reconsider this table that we used up above in example number 2. I want you to recreate this table in a spreadsheet. And here's what I'd like your spreadsheet to do. I'd like you to allow for a user to put a certain value to subtract in that cell there. So you can see that I have 8 there, but I'd like you to be able to put 10 in there or 12 in there. Any of these green cells should automatically update based on what value you have to subtract. And then I want you to compute the mean absolute error over here, that orange number that we were talking about up above. Once you have this spreadsheet working, and you'll be able to determine whether or not it's working correctly, because I've given you the mean absolute prediction errors for these different values to subtract. So you should be able to put 9 in that, and your mean absolute prediction error should be 0.625. So once you have that spreadsheet working, I want you to put 11 here and then tell me what the mean absolute prediction error is. Just go ahead and put that value in this box, answer the next question, and then hit submit. The second one here just asks you to identify potential predictor variables that might be relevant in this investigation that is described here. So you can just put your answers here. Give me an answer for question number 2. And then say submit my notes. If all the boxes have been successfully submitted or have information in them, you'll get a little green check. And now if you click on notes again, you will see my answers to each of those things that I asked you to work on. Okay, so underneath these boxes are going to be my answers to those questions. Okay, that does it then for Module 1, Part 1. Thank you and have a good day.